Today we're going to look at graphing quadratic equations. And a quadratic equation is in the form y equals ax squared plus bx plus c. We have this exponent of 2 that makes us a quadratic. And a parabola is the general shape of a quadratic equation. It's in the form of a U, which may open upward or downward. So parabola means a U shape, or parabolic is a U shaped, and that's the graph shape that quadratic equations will make when we put them on a coordinate plane. So we can use a t-table, and the most basic quadratic function in the family of quadratic functions is called the parent quadratic function, is y equals x squared. So when you refer back to how does this graph compare to the parent function, it's talking about how does the graph compare to this. So how does everything compare to y equals x squared? So we're going to do a t-table, and we're going to pick numbers around the origin that'll fit onto our coordinate planes easier. And if they get very big, they get off the coordinate very quickly. So we want to pick numbers that will fit on our coordinate plane. And we can start with like -2. And -2 squared would give us 4. So now we have the point -2, 4. And I pick other numbers around the origin, like -1. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. Then I want to put my points onto the coordinate plane. -2, 4, left 2, up 4. -1, 1, left 1, up 1. 0, 0 at the origin. 1, 1, and 2, 4. Then when I draw my graph of this, I want to draw a curved line that goes through these points. So this is the graph of y equals x squared. And we have some key features to talk about with graphing quadratics. We have this point, and this point is the vertex. And the vertex is at the maximum or minimum point of the parabola. In this case, our vertex is 0, 0. And we also have an axis of symmetry. And the axis of symmetry is the line that passes through the vertex and divides the parabola into two symmetric parts. It divides it exactly in half, and it goes through that vertex. Remember, the vertex is the maximum or minimum point of the graph. So example 1, we want to look at graphing y equals 3x squared. Then we want to compare it to the graph of y equals x squared. So first thing we're going to want to do is do a table of values. And when we pick our table of values, we're going to want to pick numbers that we're going to try to fit on our coordinate plane. And remember, when we square things, it starts to get very large very quickly. So we want to pick compatible numbers that will fit on our graph without getting too large or too small. So if we pick -2, we put -2 in, squared. -2 squared is 4. 4 times 3 is 12, so that gives us the point -2, 12. And depending on our graph, that might be a little bit too big. -1 squared is 1 times 3 is 3. -1, 3 fits on. 0, 0 fits on. 1, 3 fits on. And depending on how big your graph is, we can fit those on, or your scale. Then we want to plot the points from our table. So we go to a coordinate plane, and we want to put those points on, the points that we just found. And then we'll draw a curved line through there to make a parabola shaped. It's U-shaped. And that's the graph of y equals 3x squared. And if we want to compare that to the parent function, or compare it to the graph y equals x squared, we can say, well, both graphs open upward. They do. They both have the same vertex. They have this point right down here at the minimum point. They have that same point in common at 0, 0. They have the same axis of symmetry. If I drew a line through the middle of both those parabolas, it goes through that vertex, cuts it into two symmetric parts, so they both have the same axis of symmetry. Just the graph, our graph of y equals 3x squared is more narrow. It's more vertically stretched, we could say. So our graph was more narrow than the parent function of y equals x squared. So great comparisons on those. Let's look at a new one. Let's look at example 2. We have y equals -1/4 x squared. We're going to graph, and then we're going to compare it to y equals x squared. So we want to do a table, and when we do a table, we want to get numbers that If we square it and then divide by 4, we still want to come up with whole numbers. Decimals are harder to graph. So we kind of think about picking our numbers. If we're not given numbers for our x, if we're picking numbers, we have to pick a number that then when we divide by 4, we would get a whole number. So that gives us numbers like, let's see, -4. If I put -4 in for x, -4 squared is 16. 1/4 of 16 is 4, and times negative is -4. So we want to pick numbers that are compatible with the problem so that they make it easier to graph. Same thing with -2. -2 squared is 4, and then 1/4 of 4 is -1. So compatible numbers will make those fit on our graph really easy. We come up with whole numbers. Then we go to our coordinate plane to draw this. So we're going to plot the points from the table. And we put our points on. And this parabola is facing downward. That negative sign has made the points on my quadratic to open downward. So when we compare it to the parent function, we'll put that on in blue. We got y equals x squared. If we make our comparison, first thing we notice right away is that our graph opens downward. They do have the same vertex at 0, 0, and actually they have the same line of symmetry. The same line cuts in half. My graph, the new one, y equals -1/4 x, is wider than the original. And that happened with this 1/4 part. This fraction part made the whole graph a lot wider than the parent function of y equals x squared. All right, you guys pause the video here, complete the table. You want to use good compatible numbers to come up with whole numbers on your table, and then graph it. Pause the video here, come on back, and we'll check. Well, if I'm looking for numbers to divide by 3, I'm thinking numbers like 3, 6, 9, multiples of 3. To get this to come out to be 9, -3 works great, because -3 squared is 9, and then 1/3 of 9 is 3. 0 works great when I multiply it. 0, we put on point -3, 3 for my point. Put 0 in, 0 squared is 0, times 1/3 is 0. Gives me the point at 0, 0. And I'm already starting to see some graph come out here. So then if I put 3 in, 3 squared is 9, 1/3 of that is 3. And that's enough to see my parabola. My parabola looks like that. So what are some key features? Describe the graph. Pause the video here and make a couple examples of what you see on the graph. What does this graph look like? All right, a couple key features we have on this graph. It opens upward. It has a vertex at 0, 0. And it's wider than the parent function. It's wider than that y equals x squared we've been comparing everything to. It is wider. All right, you guys try this one as well. Y equals x squared plus 2. Well, lots of compatible points to use on this because we can pretty much square everything and add 2. But I want to pick points that are going to fit on a reasonably sized coordinate plane. If we do -2 squared is 4, plus 2 is 6. Gives me a point at -2, 6. Then I could do 0. 0 squared is 0, plus 2 is 2, so I get 0, 2. Then why not 2? 2 squared is 4, plus 2 is 6. Gives me a point at 2, 6. And I can see my parabola facing upward. So some of my descriptions of the graph, it opens upward. My vertex on this one is different. It's at 0, 2, 0 left or right, 2 up for the vertex. It has the same axis of symmetry as the parent function. However, this plus 2, what has it done to our graph? Well, it's shifted our graph 2 places higher on the y. It's shifted the parent function. It's the same width as the parent function. It's just made it 2 higher. So summary for graphing y equals ax squared. When a is positive, the parabola will open upward. When a is negative, the parabola opens downward. And when a is larger than 1, the graph will be narrower than the graph of y equals x squared. And when the a value is less than 1, the graph will be wider or more broader than the graph of y equals x squared. So use those tables, graph those parabolas, graph those quadratics that come out U shapes facing up or down. Have a great day. OUT spells out.